All right, so previously in information retrieval, we've been trying to use a probabilistic-based system in order to build an information retrieval system. It's based on the probability ranking principle that we try to return the documents in decreasing order of probability of relevance. So we wrote down that probability of relevance. We applied the magical Bayes formula in the hope that maybe that's going to get us out of this complexity and turn it into something we can actually compute. And in the middle of that, we encountered this thing right there that I asked you, what is this? And you gave the following answers, that these are the odds of the document being relevant to the query, and you're absolutely correct. I just wanted to say a few words about the last answer. This doesn't make any sense. There is no document anywhere. Well, actually, it doesn't matter, because what matters is that this is well defined mathematically, right? Mathematically, we have a random variable R, we have a random variable Q, and we can compute the conditional probability of a value of R given a value of Q, right? So indeed, these are the odds of the document being relevant for the query, document Q. All right, let me go back to the slides now. Again, if I have prepared things correctly, we should land exactly where we were. Oh, and now Zoom puts me back correctly. Okay. So if I click on here, normally that should turn it into the odds. Yes, exactly. So you see, these are the odds of relevance for query Q. Sorry, not document Q, query Q. You corrected me. Okay. So now we have that. What's next? Well, now we feel this irresistible urge as mathematicians to use our independence assumption, because now we have this probability of document D, where this small d is an enormous vector of Booleans, but we saw that we can express that based on every single Boolean in that vector of Booleans, assuming that they are independent of each other, which is an outrageous assumption that I know some of you are criticizing, and it's fine to criticize, but it's an assumption that we are making. So if we use our independence assumption, we turn this big probability into a product, right? Because this is what independence means. So we just saw that we can write this document, the probability that we have document small d, where this is a vector of Booleans, we can rewrite it as a product of Boolean-based random variables on each one of the Booleans that we have in this vector. So I go through K, position by position, I go down the vector small d, and I multiply the probabilities that the term corresponding to the position is or is not in my document. So now, here I just put it directly as a direct probability, right? But I need to add back these conditions, right? So it's for probability of document D, condition on query Q and on its relevance. So this is just the same formula. You see, if I go back and forth, that's exactly the same thing. All I did was add this and add that. But this is something you can do very often in probability theory. If you add the same condition everywhere, it just keeps working. All right, so what did I do here? Well, I'm computing the probability that given that I have query small q and the document is relevant, what's the probability it turned out to be document small d? Well, this is the product of probabilities that conditioned on query small q and the relevance of the document, that it contains this term and that it contains this term and that it contains this term and that it does not contain this term and that it does not contain this term and that it contains this term. I could go on for like billions of times. I would still be there in a year, but this is the idea, right? We just turn that into a product. All right, so now I do the same, but inside the formula, right? So I turned these two probabilities here into products, right? I just have a different condition on the right. And now I have a division of products, which, as you know, is the same thing as a product of a division. So I can just take the pi out of here, which makes me hungry. But anyway, this is a Boolean. This is also a reminder that here, small lowercase are mathematical variables and not random variables. So every time you see this, this is a mathematical object in there, right? So this is a Boolean. And we can now nicely separate, because again, if I look at this big formula here, what is it? It's dependent on small d and it's dependent on small q, right? So d here, for the purpose of this formula, is a constant. It's a specific vector of Booleans. I could show it to you if I wanted, just a bunch of. Oh, sorry. I thought I was muted since the very beginning for a moment.
No. It's just one second.
Okay. So just for a few seconds.
Yes.
So you guys on Zoom heard me. Okay. So now I just need to rewind for a few seconds. Okay. So what I was saying is, thank you, Abhishek, for letting me know. So we have this vector small d. It's a specific vector of Booleans that has zeros here and ones there. So we just partition the positions. I take all the positions that have a 0 right here. So I just condition the product on dk being 0. So I have all the case where this is a 0. And I have all the case where this is a 1. Right? So all I did is split the product, because again, this is so important. And that's the reason why I keep telling you, be careful about your notations. Uppercase is a random variable. That's a function from omega to somewhere. Lowercase is an actual mathematical variable like the ones you see in junior high school, right? Okay, so since dk is a variable, I can split it in that way. Make sense? Everybody is following? Okay, so now here's the thing. We can give that names. So I can give it a name. But of course, if I give it a name, I have to be careful to keep the dependencies. So what does that depend on? If I look here very closely in here, where are my mathematical variable? Where I have small k, that is a variable that this depends on, and I have small q, right? These are my only dependencies, because again, the uppercase ones, these are just functions, random variables. So I can give it the name pkq, and it has a specific value for every k and for every q, right? Depending what I plug in here and in there. And I can call this ukq, right? So it's exactly the same thing. What are these numbers? This is the probability that the document contains term k, given that it's relevant and the query is q. And u is the probability that it contains term k, given that it's not relevant and that it's query q. So what we can do then very nicely, this is called the contingency table, is that we can nicely consider all the cases 2 by 2, two possibilities. On one dimension, it's relevant or it's not relevant, right? Here it's relevant, here it's not relevant. So that gives us already 2 cases. And the other dimension is the kth term is present or the kth term is not present in the document, right? Not in the query, because when I cut this in there, I cut yes, I cut based on the fact that dk equals 0, dk equals 1. Suddenly I'm lost. No, we did it well. Okay, I was afraid for a minute that I got something wrong. Anyway, I have here, the reason I was confused is I was like, there are the 2 cases, but we are only on the right where the term is present. But actually it's because we are only in that column, right? If we look at this, we are in the column where the term is present, right? And here the term is present, and here the term is absent. So everything is good. So if you look at these 4 cases, relevant, present, relevant, absent, not relevant, present, not relevant, absent, then you can build that contingency table. What is here the numerator? Anybody can tell me from that table? Yes? Exactly. 1 minus p kq, and the denominator? Exactly. 1 minus u kq. So you see, if we give names to this, we also have the names here. So the 2 variables right there corresponds to this, and the 2 variables right here corresponds to that. All right. So now we simplified a bit our formula, but actually it's not a real simplification. It's just that we replace with names. We just give them names and rewrite using the names. All right. Okay, now there's a few more simplifying assumptions. So the first simplifying assumption we're going to make is specific for the terms that are not in the query. remember that the specific query we are looking at is small q. So the term k is not in the query. That means that qk equals 0. It means that in the query vector, at position k, we have a 0. The term is not in the query. So the simplifying assumption is that if term k is not in the query, so it's not even something we are looking for, we just assume that p and u are the same. So it means that it doesn't matter if the document is relevant or not relevant. The probability that the kth term is present is just the same. Now you have to think a bit, because of course it's simplifying and you could criticize and you could say that you don't agree and so on. What are we really saying here is that you query for information retrieval ETH Zurich, and you're asking yourself, okay, what about term, I don't know, butterfly, or I don't know, I want to say something totally irrelevant. The brain is not wired to find totally irrelevant things. Somehow we don't have the quantum jump to totally different space. Let's say tap water, or anything irrelevant. So you query for information retrieval ETH Zurich, and you ask yourself, okay, what about the probability that butterfly or tap water is present in my document? Well, actually, it kind of makes sense that this doesn't even depend on whether the document is relevant or not. These are not even terms you're looking for. So we kind of assume that irregardless of whether the document is relevant or not to us, the odds of finding a totally unrelated term are just the same. So this is the simplifying assumption that we are making here. First simplifying assumption right here. So we assume that P and U are going to be the same if my term is not in the query, like butterfly, tap water, if I'm looking for something in computer science. Okay. So now, what that means is that if indeed, for the terms that are not in my query, P equals Q, what is this fraction, P divided by Q? It's 1. So that means that for all the terms that are not in the query, I'm just multiplying by 1, times 1, times 1, times 1, times 1. So these I can just drop, I can just throw them away. What it means to throw them away, it means to just only keep the terms that are contained in the query. So I'm conditioning on qk equals 1, and then I just drop factors that are 1. So this is why it doesn't change the result. Is that clear? All right. So this is why, because of this simplifying assumption right here, that I now only multiply the terms that are actually in the query. This is why I add this. Okay, now here comes another simplifying assumption. And this is something that actually I have no idea why the book even doesn't mention that, because this is not what the book does, in fact, what you have on the top. What the book does is that it only uses K as the subscript. So what they actually do is they take a formula that depends on K and Q, and they say, okay, let's call it PK. Where is Q? I have no idea, it just disappeared into the oblivion. So I try to figure out, okay, why do they casually just drop Q? I saw 2 reasons for that. The first reason might be that there is an implicit assumption that these numbers here, PK and QK, do not in fact depend on Q. It means that whether or not a term is present in a document given relevance or not, maybe it doesn't depend on the specific query. Maybe it only depends on the term. Of course, that would be an assumption. And then you could also be critical and say, okay, well, if it is an assumption, why wasn't it made explicitly, right? So this is the first reason that I thought. There is another reason that might be slightly different. It's the fact that Q is turned into a constant, meaning that you compute all of these things within a very specific query. Why does it make sense? Because there are cases in that system for what is called relevance feedback, where you keep reusing the same query and trying out new results and asking the user, is that relevant or not? So that could be a second reason why they ignore the Q factor. But I really spent some time looking for that, because I was really curious, like, why do they just, it's like when you put the dust under the carpet, right? You hope nobody sees. But I didn't find. So maybe if one of you is more successful than I am. But these are the 2 reasons that I thought of why the Q is disappearing here. So of course we are going to do that for either of the 2 reasons. that these coefficients there, we assume they depend on K. They do not depend on the query, right? So it means that, for example, the probability that the term ETH is present in a relevant document doesn't depend on whether you're querying for ETH Zurich or ETH Computer Science or ETH whatever, right? It's also kind of an independence assumption, like it doesn't depend on the context. Do we have comments on the chat?
No.
Okay. Oh, it was about the sound that was cut. Okay. So this is just, okay, so I made this comment. So if you read the book again, you will not find any explanation. They just say, okay, let's call it PK. It's critical thinking is very important. So this is the sort of details you need to pay attention to when you read something. All right, so let's come back. What does it mean? It says that it means that instead of saying we call it PKQ, we just call it PK and that's it, right? And we assume it doesn't depend on Q, which it normally should because of that. Okay, so now we replace everything. This is PK, this is UK. This is 1 minus PK, and this is 1 minus UK, right? So now we have this simplified formula. Okay. So now we continue with our magical tricks. How do we improve that right there? We are going to multiply and divide by the same thing. And that same thing is this awful thing right there. So you agree, even without looking at it, if I multiply the right with this, and I divide the left with exactly the same thing, that doesn't change the result, right? You agree? I just divide by x and multiply with x, right? So I can do that. Of course, this is cleverly done in order to rearrange the factors right there. But anyway, so just to be clear what we have here. Here, it's all the terms that are present in documents D and in the query. And here, these are all the terms that are not present in the document D, but that are in the query. All right. So now I divide with 1 minus PK divided by 1 minus UK, and I iterate over all Ks that are in both the document and the query. I don't think it's necessary to understand why. You will understand based on what happens next. So just take my word for it. This is what's done. So we multiply and divide. What this is going to change here, sorry. Yeah, this is what it changes. So if I divide with 1 minus PK divided by 1 minus UK, you see the condition is the same here as it is here, right? It's exactly the same condition. We have exactly the same case that we are multiplying with. So we can associate this and this with each value of K. Since we divide, the 1 minus U goes up and the 1 minus P goes down. So this is why we have to swap there. Now, what happens if I multiply with the same thing right there? Well, notice that here, the factor is the same. So the difference between this and this is not the factor. The difference between this and this is that here, we have terms that are in the query and the document. And here we have terms that are in the query, but not in the document. So what happens to the set of Ks that I multiply on? If I multiply this, these are disjoint sets, right? So I just merge them into just the case that are in the query, right? These are just the case that are in the query and not in the document, the case that are in the query and in the document. If I do the union of that, I just get the terms that are in the query, right? And now comes the magical moment where you're going to be like, aha, I get it. Why did we divide and multiply by this very specific ugly formula? Well, look, this doesn't depend on D, bingo. Because remember what we want to do, we want to rank the documents. Now we manage to rewrite our thing with a constant factor that is totally independent on the document. So you agree that since we want to rank, we can just drop that, right? It will not change the ordering of the documents. So this is the reason actually why we did this multiply divide, right? So we throw this away. That feels good, right? When you're a mathematician and you write formulas, you just want to make as much as possible go away. All right, so this is what we care about. So you see, all we managed to do, right? We started with what we wanted to compute, so the probabilistic ranking principle. And we managed to rewrite that as a product over K, the terms that are in the document and the query, of these factors from our contingency table, right? So it's a product of weights. Okay. So now we're gonna take the log. Why do we take the log? Well, remember all these computations we were making with our standard inverted index. Remember, term at a time, query at a time. We accumulated weights into our buckets. This was a sum. What if we can turn this product into a sum? Well, we know how to do that. You take the logarithm. This is how you turn a product into a sum. So we take the log. And so that means that if you rewrite it, it's pretty much the same thing. So it's the log. Now you merge the two products. So you get this here. Now the log of the product is the sum of the logs. And you can rewrite it in that way. So now this actually starts looking like something you can even implement, because you can reuse exactly the same algorithm with this accumulation of weights that we've seen in the vector space model. And you can, for every document, you can just accumulate these weights, right? Now we can interpret that. What is the interpretation of this here? Pk is the probability that K is in the document given that it's relevant. What is Pk divided by 1 minus Pk? Anybody on Zoom? Yes, 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 I have an answer on Zoom. These are the odds, exactly. So these are the odds of containing term K in relevant documents. And the other one are the odds of containing term K in non-relevant documents, right? P is for the relevant document and U is for the irrelevant document. Okay, so this is what we are computing. Remember, just so you remember that this is the contingency table right there. So now we are left with computing Pk and Uk, right? But we are actually getting closer. So now if I call it Ck, which I can because it doesn't depend on K here, it only depends on K, according to our assumptions. This is a sum of weights with K in the query and in the documents. And again, that starts sounding like things we know, right? Because this is just a scalar product, if you think of that, right? We have C, a vector of weights for what is in the document, for example, and multiplied with another vector with zeros and ones of what there is in the query. So you can either put these weights on the document side, on the query side, right? But you agree, this is pretty much a scalar product. Who agrees with that? All right. And since this is a scalar product, we really know how to do that exactly because we've seen that. We saw it in the parametric with the zone queries and so on. So we know how to implement that into a working system. All right. So now I still have to say a few words on how we compute the weights. So of course, this will be full of simplifying assumptions, but you know, this is how things work when you implement a practical system. Okay, so you will see that computing the weights is different depending on whether you look at this or whether you look at that. Let me say it on a very, very, very high level. The number of relevant documents is usually a very small part of the entire set of documents. If you look for something on the internet, maybe you're going to have 100 relevant pages. And what is irrelevant? The rest of the internet, like billions of pages, are irrelevant to you. So that means that the first row is a very tiny part of the library we are indexing. And this here is actually enormous to the point that it's almost the entire collection. And some people actually assume, well, let's assume that not relevant is assimilated to the entire collection. That simplifies a lot of things. So this is the main message that I want you to remember. But let's dive now into the details of that. So one way to look at it, which is purely theoretical, because as you will see, it's hard to find some of the values, is to start writing not just relevant, not relevant, and present, absent, but add total columns and rows. So what is the total total? Well, the total is big N, right? It's the total number of documents in our collection. You agree with that, right? So now I'm doing statistics. I'm not, if you were doing probabilities, that would be 1, right? But here, I'm actually doing statistics. Let's try to do it based on statistics. So I'm actually counting, and then the probability we just divide based on statistics. So if we just count things, then the total number of documents would be n. I wanted to ask you that. I forgot to ask, but you will find it obvious. What is the number of documents? It doesn't matter if it's relevant or not. The total number of documents that contain term k, well, that's the definition of document frequency. Remember, the document frequency of term k is the number of documents that contain term k. So this is exactly what goes in there, dfk, right? And then this is the part that actually is harder to compute. We just call it S. This would be, for this query, the total number of relevant documents. Let's call it S. And then you start filling in the gaps, right? Here, this is n minus dfk, because this plus this must give you n. And here it's n minus s, because this plus this must give you n, right? So now, if you continue, you can call it small s. That's again an unknown. We don't know what that is, but let's call it small s. Here we have s minus s. Here we have dfk minus s. And here we have the subtraction of this, right? So you just try to fill in the table. And then that would give us these numbers. And then if you remember how pk and uk are defined, it's a conditional probability, right? So pk would basically be this divided by this, right? Or you can consider the odds as well, but basically pk would be this divided by the sum, and uk would be this divided by the sum, right? Okay, so if now I rewrite the weight that I want to use in my formula that I want to add, it's the log of the odds of presence plus the log of the odds of absence. And now I replace based on that, right? So I just, as I said, this is pk, and this is, well, just let's consider it cooking. You put the sugar, the flour, the butter, you just put it in the robot, press the button, and it mixes everything. And then you just let it give you the formula. What I'm saying here is, if you do it that way, and assuming you can compute small s and big S, you can just use that statistics that you do in that table and just compute the weight based on these statistics right there, right? So what comes next is that we do something called smoothing, because here, that is a statistical estimate, right? We assume we can count the documents in the collection, count it's relevant, it's not relevant or not, and based on statistics. The problem, it's a very general thing. It's not specific to probabilistic information retrieval or even to that course. The problem is about estimators in statistics. Imagine that you have a population. This is what statisticians call that. You have a population that is the real world. And here, these are the values that we are looking for. In the real world, it's just that we don't have access to it. So these are the values we are looking for. Now, what do? We sample. This is what people do with political polls, right? You cannot ask when you do ask the entire population 4 times a year on the voting day, right? But otherwise, you just have these polls. So when you do a poll, you don't ask the entire population. You just ask like less people. So what you get on a sample, so not the entire population, but on a sample, you get some measured values. If your sample is rather small or too small, of course, there will be a discrepancy between the two. And what usually happens if your sample is small is that you're getting a lot of zeros in there because your sample is so small that you don't even ever see some of the values that actually happen in the population. So you basically land with very few values that are non-zero and then plenty of zeros. So the way we fix that is with smoothing. We kind of add to this an equal weight uniform distribution. What if I add a uniform distribution to that and average it out? Well, I get something that looks a lot like the population again. This is called smoothing, right? So if I come back to what we had right here, I had a distribution between this and that might not be smoothed. I add a half-half, I dilute it in a half-half probability distribution. So this is what I do if I add plus 1/2, and so on. I just add plus 1/2 everywhere and dilute it a bit. That's pretty much what it is. Of course, you can adapt this 1/2 and put it to something else, right? But this is pretty much the idea, right? So you dilute it in such a way that you don't land with this biased sample, but you dilute it in a uniform distribution to get something that looks more like the population. This is smoothing. Does it make sense? It's just an intuition of smoothing, of course, right? Okay. So if I explain it in another way, imagine you want to compute the, let's say, the distribution of the use of terms over the entire internet. That's a lot of terms, right? But you only do it on 1,000 pages, right? If you only do it on 1,000 pages, maybe you are going to find, I don't know, like 10,000 terms or 100,000 terms. But you're going to have billions of terms that are otherwise on the rest of the internet, but that never appeared on the 1,000 pages that you sampled. So if you dilute that with a uniform distribution of all terms over the internet, then you fix this issue that the terms that didn't appear in your sample would have a weight of 0 if you only look at your sample. Right. This is in essence what sampling is doing. All right. Yep.
The batteries.
Oh, what's going on? Oh, I didn't plug it quick before it actually runs out of energy. It's gone. All right. Okay. So where are we? Yes, that was just a parenthesis. It was an opportunity to tell you about smoothing. But basically, the idea is that we sum over the terms that are in the document and in the query, and we add these things, and we call it the retrieval status value. It's called RSV. It's just a name that's given to it. But basically, this is the score of the document. Okay. Now, that was the theoretical thing. So this was purely theoretical, this thing, right? We just tried to fill in the tables with numbers. Now, how is it done in practice? Or actually, or how people did it in practice at the beginning? Well, some authors, Croft and Harper are their names, they suggested that if you look at relevant documents, the odds of finding a term you're looking for is exactly 1. Right. So it means that if you look for ETH, maybe half of the document you'll get have ETH and half of the document you'll get don't have ETH, but maybe a synonym, like, I don't know, EPF, let's say the French translation of ETH. So they suggest that the odds are just 1. Now you're going to think, okay, this is an ultra simplifying assumption that I'm sure even more people are going to criticize, but it's again an approximation, right? They just approximate in that way and suggest that this is just 1, and the log of 1 is, yes, 0. So I suspect they did it the other way around. How do we get rid of it? Oh, it would be nice if that would be 0. Oh, that's the log of something. It would be nice if what's in the log is a 1. Oh, let's assume that what's in the log is a 1. So that's pretty much the way you come up with this, and then you see if that can be actually justifiable. But you know, this is what happens in practice. If you build systems, you want to make pragmatic decisions, right? You want to experiment, you want to try things out. So this is how you do it. All right, anyway, this goes away. And now, and that's going to be a rabbit out of the hat. I hope that this will surprise you in a good way. The odds of containing term K in non-relevant documents, I told you earlier, the non-relevant documents usually is almost the entire internet, right? If you look at non-relevant things, it's almost everything. What if we approximate the non-relevant documents with the entire collection? Meaning we just look at the odds of containing term K in the entire collection. Now, if you look at that statistic-based estimate, it's pretty much this, because statistically, the probability of finding term K is the document frequency divided by the size of the collection, right? If you want an estimate of the probability of finding term K, statistically, it's the document frequency, the number of documents that have term K, divided by the total number of documents. The probability of not having term K would be n minus. So the odds, the probability of absence divided by the probability, so the probability of presence divided by the probability of absence is this. Now, you can also assume that n is extremely large, and the document frequency, if it's not a stop word, we can consider that we ignore stop words. It's actually pretty much, I put a plus there, it's pretty much n over dfk. What is, hey, I recognize this thing. What is the logarithm of n divided by the document frequency? Yes? This is the inverted document frequency. Exactly. You see? We just here found a theoretical explanation with simplifying assumptions that I give you, but we found an explanation and a justification for actually computing the scores as a sum of something that contains the inverted document frequency. That alone justifies that in the vector space model lecture, we have been using the inverted document frequencies. Now you have a theoretical explanation of that, right? Isn't that beautiful, the way that totally unexpected, right? All right, so we have the inverted document frequency. What we do not have, however, that could surprise you, is the TFs, right? We had the TF IDFs, right, in the vector space model. But here we just have the IDFs. Why don't we have the TFs? Well, it's our fault. We dropped them. We assume it's vectors of Booleans, right? So how do we get back the TFs? We'll do that next week with the language models. With the language models, we are going to also justify that there can be TFs in this score computation. But for now, we have recovered the IDFs. Okay. Was it an aha moment? Did you expect that? You didn't, right? Hope that was a surprise. So this is hopefully what you remember of today, that we justify the IDFs. Okay. Looking at the time, I'm almost done. Oh, good, we have a few more minutes. So, do we have a question?
Yes, there were too many assumptions in the way.
Yeah, you're absolutely correct. And again, at ETH, we encourage critical thinking. So you can look at this critically all you want, and you are encouraged to do so. In fact, this is why there is a lot of literature on other people that, maybe made less assumptions, or, try to find assumptions that are closer to reality. In the book, they gave a few of them, of your ways out. But you're absolutely correct that this might be a lot to ask, right? It gets you to a working system that you can test, but these are indeed very strong assumptions, or assumptions that you could criticize. What happens is this, though. If we make these simplifying assumptions that can be absolutely outrageous for some of them, and we build a system that uses these assumptions, it's actually a pretty good system. This is what matters. We actually build a system, it turns out to work. It even gives us this nice justification for the IDF, right? So it's really a practical engineering thing to do, right? We just try it out, oh, it turns out it works, right? That's what the discovery is here. But again, I can only encourage critical thinking. That's what ETH also keeps saying to everybody, critical thinking. So you are always welcome to criticize assumptions made in science and engineering. Did I answer your question? All right. So, sorry, catching my breath a bit. Okay. So here comes the last part now. Coming back to the way that this subscript Q was dropped from the P's and the U's, right? We just suddenly forgot that it was dependent on the query. I told you I have two justifications for that I could imagine. One of them is we assume it doesn't depend on Q. The other one is we fix Q and work just with that query Q. This is what's done here with relevance feedback. Here's what happens. So hopefully there are people who agree with the comment that you made on Zoom. Absolutely, this is a bit exaggerated. That was probably what you meant. And instead of evaluating with this set to 1, what they suggest is we just adjust that value. We try to approximate it, then we interact a bit with the user, and we fix the value. So maybe you can assume that it's 1 at the very, very beginning. And then you can start returning the results to the user. So you have the input query, you assume an initial value, maybe trivial at the beginning, and then you return results to the user. And then what happens is that you ask the user, did we do a good job? Are these documents that we return to you relevant to you? Then the user can say yes, no, yes, yes, no, yes, no. And then what you do is that you make some statistics and say, okay, you put everything here that's relevant and everything here that's non-relevant. It's just the names we give to the sets. And what happens is that based on that relevance feedback, you can look into the documents. How many of them contain term K? How many of them do not contain term K? Just looking at them. You do it for the relevant documents and for the non-relevant documents. And then you calculate, based on that contingency table, PK, but then now with S plus 1, just the next iteration, plus 1. And what you do, so yeah, this is the way it's done. You can smooth a bit, right? If you want, you can add this 1/2 and 1. Some people, instead of smoothing with constants, they like to smooth with the previous value. So they take some coefficient K and they try to give some inertia to the system, right? So this would be the new estimated value. But if you don't want to just fluctuate too much, you just tie it to the previous value and kind of merge the two, right? That's a bit like, I don't know, have you heard of Kalman filters? Maybe not. So it's pretty much like a Kalman filter. Yeah, just make sure that it stays a bit smooth. So this is called Bayesian updating. But anyway, once you have done this loop, you can update your new PK and re-execute the whole thing with your updated value. And this, I hope, also answers your remark on Zoom, that people actually improved on that, challenged the assumptions, and try to find things that actually are less simple or less trivial. Right. Does it make sense? All right. Okay. So that was my last slide. It is 3 to 4. That was master's level, as I said. There was a lot of formulas, very demanding. I'll just give you back the 3 minutes that we have left. You can have a longer break. But again, I hope that in spite of all these formulas and plenty of letters everywhere, you could still understand the high level and the intuition of it, because it's all about giving you the intuition of what's going on. And now you can read the book. It's chapter 11. So read it. Of course, you need to fix in your mind all the random variable notations to restore them to what they actually should be. But you should be equipped with everything you need to understand what's going on. Right? Okay. So thank you very much, everybody in the lecture hall on Zoom for attending. Enjoy the exercise session. And so I'll see you again next week at the same time for the language models. Thank you.